Hi, this is Aaron Wong from the University of Texas, presenting my final report on my research on the geometric analysis of 3D printed lattices through the online O-REU program at Texas A&M. My advisors have been Scott Jensen and Bradley Jared with Sandia National Laboratories. So 3D printed metal lattices have the potential of being stiffer and stronger than conventionally manufacturable structures. However, there are possible errors that can arise due to 3D printing. For example, when you slice the lattice into an STL file, the STL being the three-dimensional surface blueprint given to the printer to produce. In addition, there can be issues in print settings, or even if your settings are correct, there can be stochastic processes that occur during the print itself. At Sandia, they use computed tomography or CT scans of the lattice for analysis. The CT scans are basically a stack of grayscale images perpendicular to the build height of the lattice. Currently they are analyzed through a commercial software package that requires manual identification of major key components and provides no immediate goodness metrics. So the research objectives were to automate the quantification of the lattices and find incorrect topology automatically, meaning nodes that did not have the proper connectivity or struts that were broken or misshapen. In addition, another objective was to compare the scan of the lattice to the design of the lattice in the STL file. And a main objective was to extract the strut and normalize it, normalization meaning pointing all the struts in the same direction, so that they could be used in a future program at Sandia that will perform further lattice qualification through a feature analysis of each strut in a lattice. So the approach that I took was to take the stack of CT images, turn it into a three-dimensional representation, and then divide the project into three little groups from there. The first being just a three-dimensional visualization of three-dimensional data, providing immediate visual go no-go qualification of the lattice. The second part being comparing the scans to the STL and overlaying them to show again where the print sort of exceeded or did not produce enough. The main part was then the third part was to identify nodes and struts and extract each strut for use in for the program at Sandia. So what I found to be useful was to pre-process the image stack before creating a three-dimensional representation by creating a random sample of images and finding constants in each image. For example, the image on the left is sort of a raw image. It shows a base plate at the top that is not a part of the lattice structure itself, and also includes a large amount of area in the image that is not what is noticeable as the lattice structure itself. So the goal was to create the pink box shown on the right here. So to detect that base plate and remove it, I started by creating an average image from the sample, thresholding that image higher than usual, and then using an image processing algorithm in OpenCV called opening, which reduces an image to its largest contour. Finding the bounding box around that would then be a good estimate of where the base plate was in the image. Similarly, to find the total extent of the lattice, I used a threshold that was biased lower than usual, and used an image processing algorithm called closing, which would combine all the contours in an image into one large contour. Drawing the bounding box around that, and then subtracting the base plate, resulted in a good cropping factor, again that pink box shown on the right, that would just sort of contain just the lattice itself. From there, I could then use the cropping factor on each image, thresholded them into a binary array, and stack those arrays into a voxel representation of the lattice. I decided to use the Visualization Toolkit Library, or VTK, for visualization and 3D representation, shown on the right here. I used an isocontouring algorithm called the Flying Edges algorithm to turn the volumetric data into surface data. The main advantage of that was that I could use another algorithm in VTK called the Iterative Closest Points Transform that would be able to register one set of surface data to another. It does this by selecting a set of points, landmark points on each surface, calculating the best transformation that would map one set of points to the other, and then selecting a better set of points and iterating that transformation until it found one within a good error tolerance. So then for the third part of the project, what I decided to do was to identify nodes in the image planes itself rather than in the three-dimensional data. Then search for those struts in the 3D data between the nodes, just to search for connectivity, and then normalize and extract those struts in a later step. So what I determined was that the nodes would exist on images with higher than average brightness intensity. By finding those images and then thresholding them, thresholding turns them into a binary image shown in the blue. The blue is the threshold image of the one on the left here. And then skeletonizing them, the contour shown sort of in the middle of that blue. Taking the contours in that skeleton and reducing them to just their vertices, the points in that image, and then clustering those the clusters of those vertices would then produce a good estimate of where the node location was in that image. Repeating this for each suspected image with a node on it, for each image stack would produce the sort of point cloud representation on the right here. Clustering those together would then produce a good estimate of where the node centers were. To find the struts between nodes, I simply used an A-star path planning algorithm that would start at one node and find connectivity to the center of another node, a neighbor node. I would exhaust the search as the termination condition of the A-star path planning algorithm, and this would basically produce from the node positions shown on the left here, the sort of nodes, the struts between them shown in the middle here. So each strut is represented by a yellow and orange line, and they are sort of bound by each extreme of the path and also the volume of the node itself. So you can imagine taking the volumetric data shown on the right here, sweeping those rectangular blue squares through each path shown in orange would give you a sort of extract a strut, give you the maximum extent of the strut itself, shown in the left here. The main issue with this one is that it is not normalized, it's not pointing in a known direction, and also this extraction contains a large portion of the node volume at each flange at the ends. My approach to extracting the strut from this was then to calculate an attitude matrix of the strut, the orientation of it, rotate it such that it was pointing in the Z direction, then separate the strut from the nodes itself to produce the image in the middle, and then find cross-sections through the centroid of that strut, which were just sort of parameters required in the future program at Sandia. To calculate the attitude matrix, I simply used the matrix that would rotate the vector between node centers along the z-axis. The image on the left here shows the original node in blue and the rotated strut in red. The volumetric data is rotated and interpolated in SciPy. The advantage of this is that perpendicular cross sections perpendicular to the z-axis are easily available. And if you imagine cutting that strut perpendicular to its axis, you get a cross-sectional area, and that cross-sectional area sort of narrows, it gets smaller where the strut is and flares out where the nodes are. By finding where that area flares out is then a good indication of where the strut ends and the node begins. So then reducing the bounding box of the strut to just what contains the volume of those contours, the sort of area in the middle of the strut there, gives the bounding box shown in pink on the right here. By repeating this for each strut in the lattice, you can then extract the strut. You can extract all the struts from the lattice via the scans, and that was basically the main thrust of my research: extraction of these struts for further lattice qualification of CT data. I'd like to thank the O-REU program at Texas A&M for giving me this opportunity, and my advisors Scott Jensen and Bradley Jarrett. They've been a good help in my research here. I'd also like to thank Anthony Garland, who's another employee at Sandia, who's working on similar stuff. He's also been a really nice help. Thanks.